Good evening. Am I audible?
Good evening, ma'am. How are you?
Fine. How are you? Am I audible?
Yes, ma'am. Yeah, you are on.
Okay. Okay. In the previous two sessions, Shubham has already covered all the topics of week 9. So today, I guess we just take doubts, if any. Is that fine?
Ma'am, can you cover important topics also in today's lecture?
Important topics in the sense?
For week 9, I mean, main topics of week 9.
Okay. No, like, what is it that you want? Because everything has been explained in
Like,
the
ma'am,
previous two sessions. No?
continuity.
Okay.
This continuity, and I am clear till partial derivatives, but there is some doubt in continuity.
Okay. What about the others?
Ma'am, I have one doubt in activity question. My very first doubt.
Okay. Which one?
Oh, okay. Activity question 9.4. Question number 4.
Okay. Yeah.
Ma'am, I feel the limit does not exist for this function f of xy.
No,
Because when I check it on suppose on x-axis, I take 1, 0.
No. So the question is not limit of f of x comma y. It is f of x comma y minus g of x comma y. Did you do that?
Yes, ma'am. Okay, let it be that way. But we can calculate the limit of f of xy, then g of xy, and then subtract, because in limits the linearity formula holds. Is it
No, the linearity holds given that both the limits exist. So
yes, ma'am. First, I am checking the limit of f of xy. No?
Yeah,
I check it
you
on.
cannot
I
do
check.
that. Limit of f plus or minus g is equal to limit f plus or minus limit g, provided limit f comma limit g exists.
Yes, ma'am. First of
If
all, I am
these two
checking the
exist,
limit of.
only then you can do this. So you cannot tell limit f minus g is equal to limit f minus limit g. This limit does not exist, so this limit does not exist. You cannot tell that. If this does not exist, you cannot tell this does not exist. In fact, this is not even true.
Okay, ma'am. Then how should I approach this question?
You have to find out f minus g. First, you find out what f minus g is, and then find the limit.
Oh, I did it in some rough work just a short while ago.
F minus g will be basically 0. All terms will cancel out.
It was, I think, minus x minus y upon x square minus y square. Yes,
oh, okay, fine. Okay, then some terms, then you can simplify, cancel, and then find the limit, right?
Man, still there
minus
is some,
x minus y.
I suppose this was the answer.
Yeah, something like this only. By
yes,
x
it was minus x minus
y
on x square minus y square. Yes, this was.
So this is minus of x plus y by x plus y into x minus y.
So it comes out to be minus 1 upon x minus 1.
I think here your some sign is wrong. The x minus y term will get cancelled. That's what I remember. So the limit will be half. Yeah. So maybe if you just calculate, I think it is x minus y.
Okay.
So these two terms will get cancelled. So the limit will be half.
So the basic approach to solve this question is to that we first find f minus g and then calculate the limit.
You have already told that limit f does not exist. So you cannot use this. So you can use it only if both the limits exist. Only if both the limits exist, you can tell limit of f plus g is limit f plus limit g. Otherwise, you cannot tell this. So here you've told, no, if I don't know if limit f exists or not, but even if it does not exist, you can see that still f minus g limit exists, right?
Yes. Yes.
Yeah. Why? We can take a simple example. take 1 by x as x goes to 0, one variable function. Suppose f of x is 1 by x, g of x is also 1 by x. F of x is equal to g of x is equal to 1 by x. Now you know that limit as x goes to 0, f of x does not exist.
Yes,
Limit as x goes to 0, g of x also does not exist.
But f minus g exists because 0
yeah.
upon x.
Yeah. This becomes the zero function. So because of that, the limit exists. Okay. Any other doubts?
Okay, ma'am. One basic approach that I need to clear in question number 5, ma'am. Same.
Okay.
How should I approach this limit? Because the denominator comes out to be 0.
Yeah.
Right. So I should check this the limit on when I approach it from x-axis and I approach it from y-axis.
No. See.
Okay.
Limit exists. You have a point in R2. So if it was an R, if it was the real line, one variable limit, if you have a point and you want to approach it, there are only two ways of approaching the point, either from the left or from the right.
Yes.
That's why we had left hand limit and right hand limit. But now we are in R2, we are in multivariable calculus. So let's take R2. So if I have a point here, in how many ways can I approach this point?
Infinite ways.
Yeah, there are infinitely many ways, directions along which I can approach this point. So only if the limit along all these infinitely many directions is the same, the limit of that point exists, means limit of the function.
Okay.
As x comma y goes to whatever, say if it's x naught, y naught. X naught, y naught exists only if the limit along all the infinitely many directions exist and they are all equal. But obviously, if there are infinitely many ways, there is no way I can check that, right? There is no way I can check along infinitely many directions because it's infinite. You're not going to cover all of them.
Yes, ma'am, agreed.
So yeah, to show that limit does not exist is easy just by showing two different paths along which the limits don't match, or either does not exist or the limits are not equal. In that case, you can show easily that the limit does not exist. Showing that limit exists in multivariable calculus is very difficult. So the problems that will be given to you, there is a approach. There is an epsilon delta definition for limit and all that. So using that you can show. But yeah, that is also again complicated, which is not there in the course also. So wherever the limit, if you're asked to evaluate the limit, it means the limit exists. Because you cannot write the answer as does not exist or anything. So
okay,
when you have
3,1 in. Okay, taking this
when
question.
you have functions like this, first simplify it. Obviously, the denominator is 0. So it becomes infinity. Means, see, it's something like this, no? When you have something like this, 1 by x, then you have, it's infinity. As x goes to 0, it's infinity. So you cannot direct, so you cannot tell, in this case, yes, the limit does not exist. But suppose I had something like this, x squared times 1 by x. Then now if I cannot say that because there is an x in the denominator, the limit does not exist, right? You can simplify this term. This is basically x. So now you say that the limit is equal to 0, right?
Right.
Even in one variable calculus, we simplified it to the, we brought it to the p by q form where you cannot reduce it any further. Only then you applied the limits. So here again, you have to do the same thing. So you have x squared minus 3xy squared by x squared minus 9y power. So can you see that there is an obvious relation between the numerator and the denominator?
Take x common out from the numerator.
Yeah. So the denominator, you factorize it at like this.
X minus 3y square, x minus.
Yeah. Now is the denominator safe? Now there is no trouble, right?
Yes.
The doubling term was this x minus 3y squared. So that's gone. So now you apply the limit. So in any case, just like this x squared and 1 by x, you need to simplify it to the you reduce it to the simplest form and then substitute the values, and you will get the value of the limit.
Or
Okay,
we can use
now,
epsilon form by derivative.
Huh?
When you get 0 by 0 form, then you can
No.
derivative.
There is no L'Hospital rule here. This is
Okay.
okay, ma'am.
Done
I
it.
want to ask you. What I want to ask you, the approach is to first simplify the function and then and then evaluate the limit.
yeah, by substituting the values.
Okay, ma'am, if I can I extend this question? Suppose I have to check whether this function is continuous at 0,
Okay.
0 or no. So what should be my approach? That first I should check it from on
0,
x-axis.
0 is not at all a problem. Oh, okay. 0, 0 is still a problem. 0, 0 is still a problem.
Suppose I have to check whether it is continuous at 0, 0 or no. Right now. So I should approach it from 1, 0 and 0, 1 and check it on the line y equal to mx. Is it the right approach, or what else can be done?
Those are not the only curves. See, there are infinitely many curves. The ones that you told was along this line, and then along this line.
Yes, ma'am.
What about the other lines? Just because in these 3 lines the limits are the same doesn't mean that it is going to be the same for all the infinitely many other curves, right? So that's what I was telling. Checking limit is not easy. In this course, you will be given limits which are easy to check, like this, where you just simplify and you get the answer.
Okay.
Just because it is the same along these 3 curves doesn't mean it has to be the same along this curve or this curve or any other curve for that matter. So here, the function is not even, this is f of x comma y. F of 0, 0 is not even defined. Like, I need to give some value for this, right? Only then I can talk about continuity, right?
Right.
Yeah.
Suppose,
so maybe,
okay. Let us extend f comma 0, 0 is say 1.
Okay. So you have f of x comma y is this, and then 1 when at 0, 0. Okay. Now, what is it that you have to do? You have to do limit as x comma y goes to 0, 0. You want to check whether it is equal to 1 or not, right? So now your function is x by x plus 3y squared. Okay. Now, can you do something so that you can show that the limit does not exist? Showing limit does not exist is easier, right? You just need to find 2 different paths along which the limits are different. So maybe we can try, we have y squared here. So put y is equal to m root x. So we'll have x by x plus
I suppose them even putting 1, 0 and 0, 1 will solve the problem. Is it not?
Along the x-axis and along the y-axis. Yeah, along the x-axis, yeah, it's going to be 0. Along y-axis, it's going to be 1. Okay, yeah. So you see what I tried here? I somehow want to make all the terms have a same power so that I can cancel the terms. And I'll be left with m, right? Okay. That's what I tried to do here, right? Because if I'm left with m, it means that the limit does not exist.
Yes, ma'am.
So if you can somehow do that, then it is fine. Now suppose if it was x plus 3y, then I would have put y is equal to mx, right? So that it will be x, x, x everywhere, and then we can cancel out, right?
Madam, sorry to interrupt, but if m is equal to 1, let's say y is equal to x is what we take, it ends up as a constant, so the limit exists along that line.
Along all these lines, along y is equal to m square root of x, the limit exists along all these lines, but the limit is not the same.
Yeah. Okay, that is the difference. Okay.
Yeah. So if I had x by x plus 3 square root of y, what is the curve that will help me?
X equal to y square?
Y square. No, sorry, y is equal to x square parabola.
Yeah, mx squared you can take.
Yeah.
Then we'll have a function, means we'll end up with terms containing m. So yeah, you just try to do this. You just mostly, at least in this course, y is equal to mx squared or m root x. All these are going to be enough to show that the limit does not exist in most of the cases.
One more question may I ask on the same thing on continuity the colleague was asking.
Yeah.
Now, we know at 0, 0, it is going to go all over the place and it is no longer valid. So do I need to actually find two lines and check whether it is going to be there, the value, the same value? Or can I just go by saying at y is equal to 0, 0, it is 0 by 0 and it is no longer defined?
At y is equal to 0, it is 1, no? Means x by x.
Yeah. What I mean to say is, right, if the function itself is x by x plus 3y square, x by x 3y square, and I look at it and it is limits of x and y tending towards 0. If I substitute 0, I know it is 0 by 0 is not really going to be something which I can deal with. So
yeah,
I automatically say it is no longer continuous or it is not continuous.
No. Even here you weren't, even in this portion, you get 0 by 0, no? So that doesn't mean that you're not going to be able to deal with it. You have to see if there is something beyond that possible.
Okay, so how do I go about with continuity? I necessarily have to take lines, yeah?
Yeah, so now you want to show that this limit is equal to 1 because f of 0, 0 is 1. That's what continuity is, right? I want the limit to be equal to the value of the function at that point. So now if I approach along the x-axis, that is when y is equal to 0, I get the limit is equal to 1, right?
Yeah.
But this is not enough for me to say that the function is continuous. I want to check along some other path along x is equal to 0. So when x is equal to 0, I get the limit is equal to 0. So in this case, it is not equal to the previous limit that we obtained or the value of the function at the point. So the limit does not exist. But suppose I get this also equal to 1. Even then it doesn't say that the function is continuous, right? Because there may be some curve. There are infinitely many ways in which I can reach 0, 0. And there may be some curve along which the limit is not equal to 1.
Yeah.
And there is no way I'm going to check all the infinitely many curves. Means I cannot find out all the infinitely many curves.
Right. So we go by the, go on, please. Sorry.
Yeah, so again, showing that the limit does not exist is easy. Now here, let's take an example where the limit exists actually. Then maybe we will. Does the limit exist here? No. This one, let's take this one. So when k is greater than, so let's take x squared y, okay, x cubed y, x squared this y squared. So in this case, what do you think? Or let's take this. In this case, what do you think? Will the limit exist? No. I can put y in such a way that all the, means I already have a quadratic term in the numerator and then I have sum of two quadratic terms. So I can easily put y is equal to mx and the limit will not exist. Along each line, I'm going to get a different limit, right? Okay, so we are calculating limit as x goes.
Sorry to interrupt. How can you please explain how can we decide that we have to take y equal to mx or y equal to mx square?
So here I was telling, I somehow, if I can make all the terms, like I have an x here, if I can somehow make this term also something into x, then I can take the x common and cancel out, right? Like this. right?
And you have taken y equal to mx here, m square.
I've taken m square root x so that y squared becomes m squared x.
Okay.
I just want to make the same term appear in, means I just want to take out x and y, means eliminate x and y. If
okay,
I can
we
just
have to
make
an
it
effort. Okay, we have to make an effort so that we can eliminate the variable and see if it remains in constants, then the limit does not exist.
Yeah. So here, if I had this function, if I want to make this term as x, then I want to put something like this, right? So that when I take square root of y, I'm going to get x there.
Right.
So
now,
here, similarly, what will you do?
Yes, ma'am. Because in denominator it would be m square x square. In denominator we can take out x square common, and numerator we can take x common.
Yeah. So the degree here means if you treat x and y as just a variable without thinking of it as two different variables, the degree in the numerator is 2 and the degree in each of the terms in the denominator is 2. So you just make this simple substitution and then you're going to eliminate it, right? Then if I put y is equal to mx, I'll get what? M by 1 plus m squared or something like this. So here the limit does not exist. Suppose I had x y by x squared plus y power 4. Then what will I do?
Y is to m root over x.
Yeah, but then the numerator is not going to be affected by that. No, means I'm not going to get what? Like I'll get x m square root of x by x squared plus m squared x squared, right? If I put y is equal to m square root of x. So this is not going to help me, right?
Okay, yes.
Yeah. So what other approach can we do? So what is happening here actually? X is square root of x. So I'll have m by m squared plus 1 into square root of x, right?
Yes.
So anyway, the limit does not exist, right?
Yes.
Because along these curves, it's infinity. The limit is infinity, so it does not exist. Okay. If it was y squared plus y power 4, then
we need to check.
This is similar to this, right?
Yes, but here power is 4. Power is 3.
But I still have y squared in the numerator, no?
Yes. Denominator is greater than. That's why it doesn't exist.
No, it doesn't exist, is it? Okay. M square root of x, then I'll get x m x by or m squared x by x squared plus m squared x. Fine. So again, it does not exist. Okay. So what about this case? X squared y squared by x squared plus, or let's keep it x squared y by this. Now what happens?
Say we take y equal to m by x, m by root x.
Y is equal to m
along
by
the line that is
x.
exists, but along the curve that is doesn't exist.
Along which curve it doesn't?
I guessed it that in the numerator degree is 3 and in denominator degree is 2.
So okay, let's put this curve. I'll get m by square root of x by x squared plus m squared by x. This is not going to help, right?
Hello, ma'am.
Yeah.
Ma'am,
You can take
how you derive this equation like y is equal to m by root x, y equal to m root x. In the tutorial, it was shown that we have to check y is equal to mx.
No, see, y is equal to mx. I want to approach 0, 0. So,
If along
is the
x
point here.
along
I
y,
can approach from here,
yes,
along
yes,
this line, along a line here,
yes, yes.
or along a quadratic curve, right? Or along a cubic curve.
Y is equal
By
to
such nice functions. Along a
yes,
curve like this also I can approach, right?
yes, yes, ma'am.
So y is equal to mx is the simplest of all. They are lines passing through the origin.
Normal state line equation. Y is equal to mx.
Yeah. So in most of the cases that will help. That's it. So were you there when I was explaining this?
We can change as we wish, like y is equal to m root under x, m by root x, like.
Yeah, there are infinitely many curves, no? You can choose whichever one you want. You just want two different curves along which the limits are different.
Is there any tricks that I choose the particular equation? Is there any tricks? That is my question.
Yeah, so were you there when I was explaining this part?
Yes, ma'am.
So here I told you, no, I somehow want to eliminate the variables. That is my goal. So for that, I will make the proper appropriate substitution. Yeah.
X and Y. I want to eliminate X and Y both. Okay.
Yeah, so that they don't cause any problem because of this.
Ma'am, can you go to the last one? If we put y equal to mx, I
Yes.
get x in the numerator and I am able to eliminate the variables from denominator. That makes it quite easy. Put y equal to mx.
No, but then what is, in that case, the limit exists, right?
Yes, ma'am.
Mx cubed by x squared plus m squared.
Limit is exists, ma'am.
So in this
Sorry.
case, the limit is 0. But that's not going to help me, right? Just because along this curve the limit is 0 doesn't mean along every curve it is 0, right? These are just one set of curves.
I did that. Then what should we do?
Our objective should, as I guess that our objective should be find the limit without any X and Y. Is it?
That is to show it does not exist.
Okay, okay.
So again, that is why showing the limit does not exist is easy.
Yes, all time it is 0, then it maybe exist. Okay, okay.
So in this case, the limit actually exists and the limit is equal to 0. So showing that the limit exists is difficult. So there is an epsilon delta theory and all that, but that's not there in this course. But for it's just a way of seeing. So you see that whatever substitution you put for y, the numerator is always going to dominate the terms in the denominator, right?
My question is that there is no set rule. I continuously check for the not exist of limit for changing the equation unless until we got the how many time we will check y is equal to x square, y is equal to mx, y is equal to root x. First of all, I should check along x-axis and y-axis. After that,
and then you go for this y is equal to mx. Means the x-axis and y-axis is also covered in this, but still, you just for this course at least y is equal to mx squared or m root x. All this is going to be enough, at least for this course. And if none of these are going to work, if you give me a function right now, even with a PhD in mathematics, it is not easy for me to identify whether the limit exists or not. So even I know only these curves. Means I cannot think of more complicated curves in such a way to show that the limit does not exist.
Can I ask a question?
Yeah.
Okay, I am comfortable with this kind of function, ma'am. But if it comes like cos or sine or e power, then I'm not understanding how to check whether limit exists or not.
So when you have cos, sine and all that, okay, we will do a problem maybe in that. When you have cos, sine or e power and all that, try to write it as composition of functions. You know very well about cos x. Maybe this is what is the problem, right? This may be a complicated function, but you know cos x and you know x squared plus x plus 1. So these are two simple functions which you know. This is just a composition of those two functions. And what I know is if this function is continuous and this function is continuous, their composition is also continuous. So when you have, when you find terms which are very complicated, try to put it as composition of two simpler functions which you very well know.
Okay, but
Same
for cos, how do I do, ma'am? For expressions in x and y, I'm understanding I'll have to check along axis and along some curves. But for cos, how do I understand, or what values do I give?
Is there
for
any
cos or
specific
sine?
problem related to this cos thing?
I'm not immediately getting the activity number and all that, but I saw some problem. Can I check and tell that, ma'am, in a minute?
Yeah. By then I'll finish this.
Yeah.
Madam,
sure.
in the meantime, I have a couple of questions. So if a polynomial is a regular polynomial, that is no denominators, can we actually say it is continuous without even checking everything?
Yeah. So if I have x squared y plus y cube plus y power 4 or something like this, you know f of x comma y is equal to x is a continuous function, right?
Correct.
So f composite f is going to be x squared, right?
Right.
So composition of continuous functions is continuous.
Okay.
So for this case, any x power n is going to be continuous.
Okay.
Similarly, f of x comma y is equal to y is a continuous function.
Okay. So
I can do a composition in terms of y, and then all these are going to be continuous functions. And then I'm just adding continuous functions.
Okay. And if such a function were to be said to approach a certain xy values, I can directly substitute the values and be done with it, correct? I don't really need to break my
because
head.
I know that polynomials are continuous.
Okay. So only in discontinuous things is where we have the issue.
Suppose one thing I want to ask, you have written this cos function, right? I suppose sine and cosine functions are continuous functions. Whatever be the parameter of this function, it would be continuous and limit would be exist at every point.
No. If the term inside is also continuous, see, composition of two continuous functions is continuous. Suppose I had a function which is not continuous and I do cos of that function, doesn't mean that it will be continuous just because the cos function is continuous, right?
Okay.
Yeah.
Hello,
okay,
ma'am.
so we still haven't finished this one. Yes.
Could you go 9.4 question number 8?
Yeah, one second. Let me just finish this. So
okay,
here in this case, the limit exists. In some sense, you see there is a domination of powers in the numerator than in the denominator, right? So in the numerator, it's power 3, and in the denominator, it's power 2. Each term has power 2. So in whatever substitution you make, in some sense, the numerator is going to reach 0 faster than the denominator going away from 0, right? So the numerator is going to pull me towards 0, right? Because the power is bigger there.
But why would the numerator pull me towards 0, madam? Okay, because
That means if I want limit 0, 0.
Yeah. Right.
So at least from this course's point of view, you can look at that way. Means, yeah, if you are not able to show it does not exist, then some way like this.
So because it's order higher is where we actually settle for saying it tends to 0 faster.
Yeah. The numerator is going to dominate the denominator, so it's going to pull towards 0 faster.
And suppose it is other way around, the denominator is more powerful than the numerator.
then it's going to go to infinity. No, the denominator term is going to go closer to 0 faster than the numerator. So that will make it infinity.
Okay, that will make the denominator 0 faster than the numerator, which will give it to infinity. Okay.
Something like this. Or no, in this case,
at least it gives an intuition that.
So this is not like the theory. This is just a feeling. Yeah, this is how it is going to work. So once you get a gut feeling, you can move towards that direction, right? If you get a feeling that the limit is not going to exist, then you can look for curves where the limits are going to be different along different curves. Or if you get a feeling or some intuitive thing that says the limit exists, then you can try to prove that the limit exists. Okay, so I guess whatever we have discussed here is enough for this course. Like, it's not going to be.
One thing more I want to discuss. Suppose, ma'am, we have to get the partial derivatives and we approach it by the gradient function. So do we have to check whether
what do you mean partial derivatives by the gradient function means?
By the gradient method.
Okay. No, you want to compute the partial derivatives, is it?
Yes, ma'am.
Using gradient, how do you do that? Gradient is
directional derivative.
Oh, directional derivative. Okay, fine.
Yes, ma'am. Ma'am, my question is, do we have to check whether the function is continuous or not before using this one? Before using this method?
No. For using this, your del f should be continuous, not the function. Your partial derivatives should be continuous at that point.
Means the terms of the partial derivative, they should hold a limit.
They should be continuous at whatever point you are evaluating. Only then this will hold. So there was an example, no, where sir had that cautionary example. The last.
Yes, ma'am. That example I have not understood.
So in that example, so the theorem, what does the theorem say? If del f exists and is continuous, then directional derivative exists. So what the example that sir had given was where del f exists but it is not continuous. So the directional derivative does not exist. So both these conditions are necessary. Means you cannot leave one of them. Just existence is not enough.
Can you explain this example once again, ma'am? Because I have not understood the cautionary part. That what happens at 0, 0.
What that example was, I don't remember.
Yes, ma'am. F of xy is equal to xy divided by xk plus y square if xy is not equal to 0, 0.
Okay.
Hello, ma'am.
And 0 if xy is equal to 0, 0.
What does it mean?
Sorry, can you please repeat?
Del f exists. What does it mean? When we are doing partial derivative, then we got some variables or some output. So how to check that does it exist or not? I think most of the time not. But when I check, all times saw that the data exists.
Okay, so suppose I have suppose I get fx is equal to 1 by x. The partial derivative doesn't exist at 0, right?
Okay, yes. That,
at that point. In that sense, So whatever is the point of consideration, at that point we look at whether the gradient exists or not. This function is not continuous, right? Was this the function?
Yes, ma'am. It was a function.
Okay, fine.
In the example.
Okay, so what is fx? Fx of x comma y when x comma y is not equal to 0. You just differentiate with respect to x and all that. So x squared plus y squared whole squared, squared plus y squared into y minus xy into 2x. So if I take y common, I get y squared minus x squared. Right? This is f of x comma y. What is this is fx of x comma y. What is fx of 0, 0? How do we calculate this? Here we should go by the definition, right?
Yes.
Yeah. H goes to 0. F of 0 plus h comma 0 minus f of 0, 0 by h. So f of h comma 0. So that's going to be 0, right?
Yes.
Yeah. So now the partial derivative fx exists. Okay, similarly we get some fy. Okay, so we are getting some fy. Let's not calculate. So it's going to be something, something. Fy at 0, 0 will be 0. This is going to be some term, whatever is the term. So my del f is going to be fx comma fy. And then what is the directional derivative? So directional derivative is going to be fu. Let's take u to be a unit vector. So this is limit h tends to 0 f of x plus hu1 comma y plus hu2 minus f of 0, 0 by h.
Why don't you take the dot product as explained in the lecture?
No, you're not allowed to take the dot product because the function is not continuous. No, the gradient is not continuous. So that is the problem. No, you have to calculate it separately, and then you should check what is the problem that's happening.
Okay,
yeah.
That's why we are going by this first principle.
Yeah, the definition. Yeah. So actually the function, this is not continuous at 0, 0. So I guess we'll calculate at 0, 0. That will be easier.
Can I pause you for a moment? How do we know that function is not continuous? Are we taking the example or we are checking somewhere that function is not continuous?
So we calculated fx at x comma y for x comma y not equal to 0. And then we checked fx at 0, 0, which is 0. Right?
Not getting it, man.
So, no, this we calculated just now, right? You got how we calculated fx, right?
Yes.
We just kept y as a constant and then differentiated with respect to x.
Yes,
we also calculated fx at 0, 0. So, fx is this function for me now. Right? This is my fx.
Yes, ma'am.
If I want my gradient to be continuous, I want both fx and fy to be continuous, right?
Yes, ma'am.
So is this function continuous?
That we have to check by finding the limit.
Can you do it quickly? So you see that there is a dominance in the denominator, right? It's x power 4 in the denominator and just x cube with the, even if I put y is equal to mx.
Yes, ma'am.
It's going to be so you see there's a dominance.
It seems that the limit would not exist.
Yeah. Limit x comma y goes to 0, 0, fx does not exist. So this function cannot be continuous, right?
Okay.
Yeah. So this function is not continuous. Now I needn't even proceed to fy. I know that this gradient is not continuous because one of its components is not continuous. Right?
Hello, ma'am.
Yes, ma'am.
Yeah.
When you try to find limit, find the limit exist or not. So that time we need to check that is continuous or not. I think.
If you first find the limit and then you check whether it is continuous or not. If all the limits exist and it's equal to the value of the function at that point, then it is continuous.
Okay, ma'am.
Yeah.
Madam,
So,
one fundamental question here.
Yeah.
When you are computing it at fx 0, when it is done, when the differentiation is done for partial differentiation is done on the x, we are adding h to the x term and not the y term, correct? It's because we are differentiating on the x. Okay, that was more.
That's the definition.
Yeah. Okay.
May I ask one question? What is the best approach to check the content that we have to check by the definition? Is it the best approach?
So here you have a split, right? F of xy is something for some points. It's 0 for this point, right? So you cannot tell fx of 0, 0 is equal to dou by dou x of f of 0, 0. This is not correct, right? Okay, dou by dou x means I am differentiating this partially with respect to 0. Okay, in this case it is the same. You have 0, you differentiate 0, you'll get 0. But this is not correct. Because when you talk about differentiability, as this h is going to 0, what happens to this 0 plus h?
Yes, ma'am. This is what I mean, that we have to check by the definition, right? Like f of a plus h minus f of a upon h. We have to apply this definition while checking.
Yeah, because when you're finding derivatives, you're actually looking at points nearby the point you actually want. Means if it's 0, 0, I'm looking at points nearby 0, 0. And at points nearby 0, 0, the definition is completely different, right? You have to use that definition. So you have to go by the actual limit thing.
Okay.
Yeah. Okay, so now I have del f is not continuous. And then the partial derivatives, something I remember, it was something like this, right? u1, u2 by h or something, right?
Yes, ma'am. Being h in the denominator and the limit would not exist.
Yeah, it will not exist provided u1 and u2 are non-zero. If one of those two are 0, then the limit is 0, right?
And then should it not be 0 by 0 form? How can we say that? If suppose u1.
See, what is limit of 0 by h as h goes to 0?
It would be 0.
Yeah. This is not 0 by 0 form because the function is already 0. Even before applying the limit, the function is 0.
Okay. Okay.
Yeah. So, all the directional derivatives exist other than the partial derivatives. So,
how do we say that, madam? Because
no, this limit exists if u1 comma u2 not equal to 0, right? Oh, it does not exist. Sorry. Does not exist.
Yeah.
So only fx and fy exist, correct?
But,
fx means what? u1 is 0. Fy means u2 is 0. Right? How do you get fx? The unit vector is 1, 0. How do you get fy? The unit vector is 0, 1. Right?
Yes.
Yeah.
But
so these two exist.
But it's already established that it does not exist, right, up there? F of x does not exist.
It exists. It is not continuous. Not continuous. Fx is not continuous. Means fx exists. We have found the derivative.
Right.
So this is fx. Fx exists, but it is not continuous.
Okay.
And this means that when we get this gradient vector or gradient function, then we have to check for its continuity.
Yeah. The continuity of the gradient just means continuity of both the partial derivatives.
If the gradient is continuous, then we can calculate the directional derivatives.
Yeah, using this formula.
So let's assume f of x is continuous. We check for f of fy, and that also exists and is continuous. Then
I can use this formula to find any directional derivative.
Okay.
At whatever point it is continuous, you can use this formula. At points where it is not continuous, that is where the problem lies.
Sorry, once again. At points where it is not continuous, we cannot use. But does it mean when we earlier the conditions that were mentioned were it should exist and should be continuous. So if it is not continuous, we cannot use them.
So
right?
this all these theorems.
Yeah.
We are talking about a particular point. Del f exists at what? At a comma b and is continuous at a comma b. Then the directional derivative exists at a comma b. So it is all with respect to that particular point we are talking.
Okay. So all right.
Yeah.
Okay.
So wherever it is continuous, at all those points where it is continuous, you can use this formula. No problem.
Okay.
Okay. Someone was asking 9.5 some question.
9.4, question number 8, option 3. Okay, 9.4, ma'am.
Question 8, option 3.
So in this question, I need to, yes, I done this. In this question, we need to find false option. So option 3, so their left hand limit and right hand limit doesn't equal. So that is the correct options. So in the answer sheet, that is given the wrong answer.
Limit of the given function at 0, 0 exists.
Exists but not equal. Left hand limit and right hand limit are exist but not equal.
No. The question is not about left hand and right hand limit. Limit of the given function. So all the infinitely many paths you should consider. So you have done problem 6 and problem 7. So you're getting different answers, right?
Yes.
So the limit does not exist, right?
Okay, I thought. Okay, got it.
Yeah. Someone else also had asked some activity question previously.
I think the question
regarding the sign thing, it's there in activity 9.5.
Okay, this one, right?
Yes.
Okay, so here you want cos y sines when x is not 0. Okay, so now you can split this like this, right?
And what we have to do in this question, we have to calculate the limit. What is the question?
Yeah, something. F is not defined at 0, 0. Obviously, f is defined at 0, 0, right?
Yes.
Cos 0, when x is 0, you use the definition cos y. And
that is
cos
also
0
continuous.
is a well-defined number. Yeah. So f is defined at 0, 0. Is f continuous at 0, 0? So if f has to be
simple cosine
continuous
function
at
is
0,
continuous.
Madam, sorry to pull you back. Can you explain the earlier statement once again, madam? At 0, 0, it is defined. You picked f is defined at 0, 0.
So when x is equal to 0, you have to use this definition, right? Cos y.
Yeah.
And cos y is a continuous function, right?
Yes.
So cos 0, the value is going to be cos 0.
But what values should I use for y is not really known, right?
No. 0, 0. What is f of 0, 0?
Okay. All of them are f of 0, 0. Okay. Cos y is 0. Okay.
Right? It is going to be cos 0, 1, right?
Oh, there is 1, yeah.
Okay, ma'am.
So
If one of the please.
I want to show this is equal to what? F of 0, 0, that is equal to 1. I want to show this, right?
Yes, ma'am. Limit value is equal to function value.
The value of the limiting value is equal to the value of the function at that point. So I have cos y sin x by x. So I can split it like this. And then limit.
Okay. Then we can use the product rule.
So I can do this. There are two different functions now, right?
From maths 1, then this is sin x by x limit. This is 1 sin x by x.
Yeah, there is no y at all here. So this is going to be a function of one variable. This limit is 1. This limit is 1. So the product is 1. I can use this only because both exist. Otherwise, I wouldn't have been able to do it, right?
So if one of them were to tend to 0, then it is all gone again, right?
No, 0 is fine. 1 by 0 is not fine.
Okay.
What is the limit of this function?
1.
Yeah, but I cannot tell this is equal to limit as x tends to 0 of x and limit as x tends to 0 of 1 by x, right? I cannot tell this. Because this limit does not even exist.
Correct.
So you can do the product rule given that both the limits exist. Just like how the sum thing worked. We can do the sum thing, the rule for sum, given that both the limits exist. So here we have both the limits exist, and hence the limit is going to be 1. Ma'am, is it clear?
Yeah, for this problem, I'm clear, ma'am, but I'm not, as I understand the polynomial function, I'm not able to clearly understand how to check for limits when it comes to sign. Or...
Okay, is there any other question related to this sign?
In the same question number 4, ma'am. Question number 4.
Question 4. This is log. Okay.
That is direct question.
Yeah, this is just continuity. No, you just have to check where each of these functions is continuous. Vector value.
Ma'am, could you explain question number 9 of that activity?
So whoever asked question 4, is it fine? It's a vector valued function. So you have to check where each component is continuous. And then you take the intersection. That portion is where the entire function is continuous.
One second, madam.
Okay, thank you.
Yeah.
Can
so if
just
you have
say
components,
yes,
if you have a vector valued function, you have to check where each of the components is continuous. Where is the function 3t continuous?
1 by t continuous, okay.
3t is continuous everywhere. 1 by t is continuous everywhere other than 0.
0.
Log 1 minus t is not even defined when 1 minus t is less than 0, right?
Yes, ma'am.
Yes.
So for each function you have to check component wise. Question number 9. Okay. So what is the problem in this question?
I can't find the answer. So here is given dot product comma minus 1. So how to find continuity of this? Because here is
so you have a function like this, f of r. It's a scale, it's a function of one variable, right?
Yes.
Norm r squared minus 1, right? And the product r comma r is norm r squared, right? R is x comma y comma z. So basically f is a function of x comma y comma z, right? 1 by square root of, or not square root, 1 by x squared plus y squared plus z.
Hello ma'am, here is a dot comma -1, not -1. If it is a -1, then I can solve it.
Oh, this is there's a comma here. There is no comma.
Yes, yes.
It should be this. There's no comma and all here. It's norm r squared minus 1. So you just put the denominator to be 0, right?
Okay. I thought here is a comma. That's why I can't find.
Okay, we change that. Okay, 9.4. Someone was asking some question in 9.4. I remember seeing some cos and sine function with the term inside cos being something difficult. 9.6.
I think 50 assignment. There is some question.
Which one? Practice.
Practice exam.
What about this one? So, ma'am, you were talking about sine and cos and dealing with it being difficult, right?
Yeah, but I have not gone through this activity yet, ma'am.
Okay, you can check this problem. Shubham had solved completely in the previous session, so you can try this out, and then if you're not able to do, you can watch that session, just the previous one.
Okay.
So how to calculate partial derivatives.
Okay.
Practice.
Madam, partial derivatives is just fine, but if we really have to compute the limit for this function.
Which function?
The 9.68. If I had to compute the limit as x tends
It's a
to
very
0.
difficult process, so you can ignore that. It's okay. One thing you can do is you can do sandwich. The function is continuous. Okay, the question is whether the function is continuous. So you can use sandwich theorem, right? This is less than or equal to x squared plus y squared.
Ma'am, may I pause you for a moment?
Yeah.
Where do we mainly apply this sandwich principle? It means that where numerator and denominator each, we don't have a negative sign, right? Then we can say for sure that we can apply the sandwich principle. If one of the signs is negative, we are not sure. No?
Yeah. So that's why I took modulus. So now modulus of f of x comma y goes to 0. Limit is 0, right? Because
do you
this
need
goes to
mod?
0. Mod is not there in the question.
Yes.
But without mod, I cannot tell this, no? Oh, I don't think we need mod, right? Okay.
Why don't we start from say
minus of x squared plus y.
X squared plus y squared.
Right?
Okay.
This goes to 0, this goes to 0. So we are done.
Sorry?
We want limit as x comma y goes to 0, 0, right?
Right.
So I know that the maximum value sign can take is 1 and the minimum value it can take is minus 1.
Correct.
So the minimum value minus of x squared plus y squared, the maximum value is x squared plus y squared. Now if I take limit as x comma y goes to 0, 0, this term goes to 0,
Correct.
this term goes to 0. So by the sandwich theorem, this term goes to 0.
Can you show the question, please?
Okay.
No, the question didn't ask this. The question was some partial derivative.
So basically, because I know the range of values of sine, I can come to that conclusion. Is that the correct way of interpreting? Okay.
Yeah. In fact, this would have been possible for any bounded function, right? Not just sine. Any function which has some number. Only if it's going to infinity and all, I will have a problem. If there is a small number and a big number, yeah.
Well, in this question, what we are doing that we are calculating partial derivative on x-axis and on y-axis, right?
Yeah.
By putting 1, 0 and 0, 1. Is it the same.
No. What is 1, 0?
Ma'am, along x-axis.
So you will do this. Limit as h goes to 0, f of 0 plus h comma 0 minus f of 0, 0 by h. So you will calculate this.
Ma'am, why don't we put 1, 0? Because in calculating the partial derivative with respect to x, we have to take y as a constant.
Yeah.
And we put 1,
1, 0. The direction is 1, 0. So you have to put 1, 0 in the formula for directional derivative. So that's going to be 0 plus 1 times h, comma 0 plus 0 times h minus 0, 0.
Okay, this is the definition, right? But
this
in one of the lectures,
derivative.
In one of the lectures, sir has told that you can differentiate, calculate the derivative by treating y as a constant.
That's what we did earlier, no? How did we calculate fx here?
Yes, ma'am.
By treating y as a constant.
And we can use this same approach in this question here.
Yeah, but you want it at the 0, 0. No, at the 0, 0, what's the definition of the function? It's not given, no?
Okay, at
0, 0,
we have
there is a problem, right?
Yes. Yeah. Then we have to use the definition only. And how we are using definition in this one? Can you explain one part, please?
Here. So you put this limit as h goes to 0. Y is 0. X is h. So h squared sine 1 by square root of h squared by h. So this limit is h. So here I have 1 by h. So sine 1 by h by 1 by h.
By 1 by h. It is 1.
No. H goes to 0, no? Sine theta by theta
is 1.
Goes to 1 as theta goes to 0. But I have the other way around. Sine 1 by theta. Sine theta by theta as theta goes to infinity. This goes to 0, right? Why does this go to 0 as theta goes to infinity? I can write the same. This goes to 0, this goes to 0. So this goes to 0. Sandwich theorem, right?
Okay, ma'am, you can first written like sine theta lies between -1 and 1 divided by theta. And sandwiched it. Okay.
Yeah. So here I have similar to infinity thing, 1 by h. So this is infinity thing, so this limit is 0. This is equivalent to sine 1 by theta by 1 by theta goes to 0 as theta goes to 0, right? And this here it's theta goes to infinity, theta by theta. Here theta goes to 0. So 1 by theta will go to infinity, right?
Yes, ma'am.
Yeah.
Hello, ma'am. Could you go question number 9?
So, ma'am. Hello, ma'am.
Yeah.
Hello. So, ma'am,
yes.
such type of piecewise function, we should only use definition of partial derivative only. Such type of piecewise.
Wherever there is a split, yeah.
Yeah. Okay.
Question 9, okay.
Yes.
So did you calculate partial derivatives?
I can't.
So again, fx at x comma 0 is limit as h goes to 0, f of x plus h comma 0 minus f of x comma 0 by h. So this is limit as h goes to 0. Or you need to do all this. At 0, 0 only there is a problem. So you can just calculate fx at x comma y and put y is equal to 0, right?
Okay.
Because if simply y is 0, there is no problem. Right?
Okay.
Yeah. So you do the usual thing and then put y is equal to 0. Whatever answer you get, that will be the answer. This also Shubham has done in detail. You can check that.
Okay,
you can try it out on your own, and then if you're not able to, then he has done.
Okay. Question number 1, ma'am.
Okay.
I have
1.
Yes, 1 option 1. So here after codomain is R.
No. If the codomain of F is R, the question is about del F.
Okay.
So F is a function of 3 variables. So how many components will the gradient have?
3 component. Yes.
Fx, Fy, Fz.
Yes. Got it.
Any other questions?
Yes, ma'am. Practice assignment question number 6 and 4. How to find limit of limit? Question number 4.
Okay. Did you check the solution?
Yes, I checked it. I can't understand limit of limit. So how to find that?
Where is limit of limit? So here limit of
Option
limit is much simpler than limit of x comma y, because here you have to treat it as a function of one variable, apply the limit, and then go to the next. Okay, let's.
Could you solve?
So you found out G composite F and all that. Okay, 1, 2, 3, 4. Fifth option is what you want, right? Or let's do sixth maybe. That's simpler.
Okay.
Just G of F. X squared minus y squared, x squared plus y squared. Okay, so limit as x goes to 0. What is limit as y goes to 0? G of x comma y. So there is no effect on x. You just want limit as y goes to 0. So what will you get?
Limit y goes to 0 is 1.
No, x squared by x. Okay, yeah.
It is 1. I have calculated.
So this is a continuous function. This is a continuous function. There is no problem at 0. So you just calculate, you directly substitute the value and get this, right?
Okay. Direct substitution.
Yeah, because there is no problem. No, only if there is a problem, you have to find out some other method. Otherwise, substitution is the way, right?
Okay. Got it.
Then what about the limit x goes to 0 outside it?
That's all. No, we have already got 1. No.
Then,
So whether x goes to 0 or infinity, it doesn't matter. No.
Okay.
Then sixth problem. So can you do this also now? Yeah, there is a function given, no, in the solution.
Yes.
None of these imply. There is no relation between existence of sequential limits. So here you just apply the limit twice, and then continuity where we talk about x comma y goes to a comma b. So here, if this is a comma b, what you do when x goes to a is you move along this line. and then you move along this line. So this is just one of the paths to reach A comma B, right? This is X goes to A, this is Y goes to B. If I go this way, this is Y goes to B, and this is X goes to A. So these are just two of the paths, but that has no relationship between the continuity. Means there are infinitely many paths. So maybe they are all different. So that is what that example says.
Okay.
Where none of this holds. And in one variable calculus, we have differentiability implies continuity. But here the existence of partial derivative does not imply continuity. There is a notion of differentiability which will come in week 11. So there you will see differentiability implies continuity, but existence of partial derivative doesn't guarantee that the function is continuous.
Okay.
Ma'am, this is what we have seen in the while calculating the gradient, right? We can calculate the gradient, which is the partial derivative along x and y. But that does not guarantee that this is continuous. That we have to check using the definition.
Madam, I have some fundamental question again. Sorry.
Okay.
Normally, when we are actually trying to compute the limits, we are saying we take it as f of x plus h minus f of x by h, and then say h tends to 0. Correct? Yeah.
Now, partial derivative, right? What you said was for partial derivative.
It's only f of x that, I mean,
you said this, right?
Yeah, yeah.
That's for partial derivative.
No, I'd not say 0. I'd not say 0. I said only x plus h minus f of x. No y involved. No y involved.
Oh, okay. This is the derivative. Okay.
This is the derivative. Now, when we are actually using a function which is having both x and y, and I have multiple combinations, not multiple, at least 4 combinations of having h or no h and all these things, right? I can have h on one side, I can have h for...
No, you have infinitely many, no? That is where the directional derivative comes into picture, no?
Right,
u1 h, u2 h. So you have infinitely many, in fact.
Right.
And then?
So if this limit actually solves for 1, it need not necessarily be the value of the function. Yeah. Okay. Got it. Thank you.
So there is something similar to this in multivariable calculus, differentiability, that you will study in week 11.
Oh, okay.
Yeah.
Hello, ma'am. 9.6, question number 7, option 4. Option 4. Not 4, ma'am. Question number 7.
I'm just looking at the function. Y cubed by x squared plus y squared. Okay.
Not question number 5.
Did you calculate the derivatives?
Yes.
Which one did you get?
Question of I think option 1. Option 1 and option 3.
Okay, fine. Something. Okay, fine. What do we want to do? Discontinuous at origin.
Question number
From
5,
option 3, 5. It is option 5.
Yes. Option 5. I didn't understand.
Directional derivative of f in the direction of the vector A at 0, 0 can be obtained using. So you use option 4 for it.
Yes, option 4 is incorrect. That is correct. Discontinuous.
So you cannot know. So this is the theorem, then... application of that theorem.
Okay.
This one.
Okay.
So the theorem doesn't say that if it is not continuous, the directional derivative does not exist. It only says that if it is not continuous, you cannot use this formula. That's it.
Okay.
Yeah.
Gotcha.
No, actually, I had a doubt in 9.4 last question.
Okay.
So basically, when it is like k, it's smaller than 2n minus 1 or greater than 2n. So how do you approach this, or how do we calculate the limits? So like, do we add something to that, or?
No, this is similar to what I was explaining. No, the trick of how to choose the curve and all that.
Yeah, so
Similar.
basically we substitute y is equal to mx or m root x, something like that. But that 2n minus 1, so how do we do that? Like we should
So
take
if
it.
this is, so this is suppose 2n minus 1, then the numerator, the total power is 2n, denominators also I have 2n, so I'll put y is equal to mx and then get that the limit does not exist, right?
Yes.
So suppose it is less than 2n minus 1, say it is 2n minus 2.
Yes.
Let's take a particular value in fact. Put n is equal to 1. So 2n minus 1 will also be 1. So I'll get xy by x squared plus y squared.
Yes.
Not equal to, I want less than, right?
Yes.
Okay, so x term will be gone. So I am choosing x power 0. Okay.
Okay.
So in this case, you see that.
Yes, sorry, go ahead.
So you see that there is a domination of the denominator term, no? So this goes to infinity.
0.
That's not infinity.
Yes.
So if you have some term which is less than 2n minus 1, 2n minus 2, say, if I put whatever value of, like if I put y is equal to mx squared, then I might get x power 2n in the numerator. But then when I put y is equal to mx squared here, I'll get x power 4n, no?
Yes. Yes.
So again, there'll be domination in the denominator, right?
Correct. So basically now if it is greater than, then we will simply do 2n or 2n plus 1 like that.
Greater than means
if k is greater than 2n, then it will be like
then
2n
the terms
plus
in the
1.
numerator have higher power, so they will dominate. So this will go to 0 faster.
Okay.
Yeah.
Okay. Thank you.
Any other doubts?
Madam, I have one more doubt. Like you mentioned earlier about, let's say there are two variables which can be split a multiplication. Cos
Just
theta.
one second. Quiz 2 portion is 1 to 8, not 9. But 9 is counted for eligibility for end term, right? One to 9 weeks eligibility for end term, right? I guess so.
Ma'am, you mean assignment submission?
Graded assignment submission.
Yeah. Submission is necessary.
1 to 8 is quiz 2 portion. Okay. Yes, sir.
So there doesn't count 9 to 10 to 11, 10 to 12.
So if you qualify for end term, then even if you don't submit 10 and 11, it's okay.
Okay, if I qualify and then submit the remaining assignment, there will be called count.
Yeah, your score will improve, right?
Okay.
Yeah.
That is fine.
Madam, like what your trigonometric function that you solved, one of the problems there, cos theta sine theta by theta or something, which you actually split it out saying cos theta into sine theta by theta and applied the limits on both the terms separately.
Yeah.
If I have a polynomial, like let's say x square minus 1 into e power minus 1 by x or something like that, can I actually multiply it as x square into e power 1 by x and
e power 1 by x. Okay.
minus 1 by x, let's take it as. Okay. So can I make
you
two
want
terms out of
limit
it?
as x goes to?
X goes to 0.
Okay.
Can I?
There is no problem, no? Means you can write it as limit as
Flip
x
them up,
goes
is it?
to 0.
Yeah.
Limit as x goes to 0, e power minus 1. E power minus infinity, what is e power minus infinity? 0, right?
0.
So this is also limit exists, this also limit exists, so no problem.
What I mean to ask is, okay, for this function, can I write it as, can I potentially write it as a x square e power 1 minus 1 by x and minus e power minus 1 by x, and then separately compute the limits?
Yeah, you can do that also. Because the limit of this also exists. Minus e power minus x. Limit of this exists, limit of this exists. So you can write it as 0 minus 0 equal to 0.
And even if I take it as e power 1 minus 1 by y also, I can do the same, right?
In that case, I think you have to be careful because x squared e power minus 1 by y along x-axis, y is going to be 0, so this is going to go to 0. Then along x-axis also is going to be fine. But how do I proceed? What is the argument? Oh yeah, here we can use that argument. No? Limit as x comma y goes to 0, 0 squared
into e power minus,
yeah, you can do that.
I can separate them out and then use the multiplication here and the addition over the next term, that is minus e power minus 1 by y, right?
Yeah.
Thank you, madam. Thank you very much.
Oh.
Ma'am, can you please explain the concept of continuous again? Continuity.
Okay, continuity is simple. What is continuity in one variable calculus? So you want limit as x tends to a, f of x to be equal to f of a, right?
Yes, ma'am.
As we go closer and closer to this point, the value of the function should get closer and closer to this point. It's the value of the function at that point. So it's the same here also. X comma y goes to a comma b. F of x comma y should be equal to f of a comma b. But the only difference between this and this is, here they're approaching this. There were only two possible ways of approaching, left hand limit, right hand limit.
Right hand limit.
Here we have infinitely many curves to approach this point. So along all those curves, the value of the function should approach f of a comma. That's it.
Okay. In this we calculate the limit along x-axis, along y-axis, or along the line. If the limits are same, then the function is continuous.
No, you cannot tell that. So there are infinitely many curves. No, you have checked only finitely many. X-axis, y-axis. Okay, even if you have take all the lines, there are so many infinitely many curves which you have not checked.
Yes,
right?
ma'am. Yes, ma'am.
Yeah. So that's why
then
showing continuity is difficult.
Okay. Then what is the correct method to find the continuity?
So you can, there is one thing called as epsilon delta method, which is not there in the course. This is like pure math. So using that you can check. Even that is difficult, but that's better than what methods we have in this course. But for now, this much is enough. Whatever we have discussed.
Oh, ma'am, can you repeat, please?
Yeah, so there is something called as epsilon delta method.
Yes, ma'am.
So you define limits using epsilon and delta. So using that, you can check continuity, the actual definition of limit. But that's not there in this course, so you can ignore that.
Okay.
Yeah, that's pure math, so you can ignore all that. That's rigorous mathematics. For this course, whatever we have discussed here is enough, and using these little tricks or something, you can tell whether it's continuous or not.
Like the questions given in the activity questions. So how could we find here the continuity?
So we were discussing, no, something similar to this. If the numerator terms are overpowering, using
Actually,
that.
I missed that.
Okay, so maybe you can watch it again, because if I tell just this portion, you might not understand. There is a lot of things before this also that I said. Were you there when I explained this problem? This one? Maybe you just watch this portion again. This portion.
Okay.
Yeah.
Okay, thank you, ma'am.
Any other questions?
I have some more. I hope I'm.
Grading pattern. I have no idea. You should check it. Yes, sir. Please go ahead.
Yeah. When we are actually finding the directional derivatives, we add the h, x plus h and y plus h and look at that. That is the derivative part of it. When I'm looking at the limits, only computing for the limits, do I still use the h or not necessarily?
No. What do you mean by limit this, right? Limit of f of x comma y goes to 0, 0, or something, a comma b, right?
Correct. Yeah.
So when the h part comes, because there is a change in some direction. Here there is no change or anything. No, you just want to find the limit. The h that we use actually denotes increment or change. That is why we are doing that x plus h comma y. There is a change in the direction of x. But limit is not like that. No, you just have a function. What are you actually doing? There is a point. Okay, I cannot draw for two variable functions because the graph of a two variable function will be in R3, right?
Yes.
Yeah. So let's take a one variable function.
Yeah.
So I have a point A, and then this is my function f of x. What am I actually doing is I'm going closer and closer to A from both the possible directions.
Correct.
And I want to make sure that so the value of the function in this interval is going to lie here. And the exact value is this, f of A. So I want to make sure that as I get closer and closer to A, this interval gets closer and closer. F of the interval is getting smaller and smaller. Means the image of this interval gets closer and closer to the value I'm looking for.
Okay.
This value. So the same thing happens here also. We'll have it in 3D instead. So as I get closer and closer to x comma a comma b. So in two dimension, my interval becomes circles, right? Open balls.
Yeah.
So as I get closer and closer to this, as I make this circle go smaller and smaller, I want the image of this circle to get closer and closer to f of a comma b. That's continuity. If it's some random number L, then that's just the limit.
Okay.
Yeah. The H thing comes when you want to talk about change.
In a particular direction. Okay.
And when change comes into picture, that is when derivatives happen.
So when I'm looking at limits only, I reorganize my variables whichever way is convenient and substitute the values of A and B directly.
Yeah.
Thank you. Thank you.
Okay. You can maybe quickly watch the other two sessions also and then solve the paper.
Sure. Thank you.
Okay, if there are no questions, then can we close? Tomorrow we will discuss. There's a revision session tomorrow.
Tomorrow?
Yeah, tomorrow, right? 6.
At what time, ma'am?
8 o'clock.
Okay.
Tomorrow and Friday. Friday our usual timing. Tomorrow at 8 o'clock.
Okay.
Maybe you can quickly revise as much as possible.
Okay.
Maybe try to extend tomorrow's session a bit because Friday 6 to 8 and then 8 o'clock there is stats too. So Friday we might not be able to extend. Instead tomorrow we will try to extend.
All right.
So do you want to revise anything from week 1 and 2? No, right?
Okay.
We can start off with vector spaces probably.
Yeah, that would be good.
So tomorrow maybe we will plan up to vector spaces, basis, rank nullity theorem, linear transformation. And then,
excuse me, ma'am.
Yeah.
Madam, linear transformation. Sorry, go on.
That should revise big.
Sorry, can you please repeat? Your voice is breaking.
Ma'am, take session as a revision of week 1 to week 4.
No, what I was thinking is week 1 to week 4, if we split it that way, we will not be able to concentrate on the new portions. No, week 1 to week 4, we have already discussed a lot. So maybe what I had in mind was 1 and 2 is simple. So yeah, we'll start off with vector spaces.
Easy, ma'am. Let's start with vector spaces and bases and spanning of sets and that.
We will do up to linear transformations or something. And then Friday we will discuss kernel, range, equivalent matrices, similar matrices.
Yes.
And week 8 also is simple, I guess, right? We don't need a revision for that.
Yes, ma'am.
Gram-Schmidt process and all, it's a formula that you have to remember. So,
Madam, would you be able to?
Quiz to the major portion will be of week 6 to week 8. Week
no,
5 to
1
week
to
8.
4 is week 5 to week 8. So it's not like, I'll not say major portion because given a question, you will be asked to find a basis and then proceed. So if there is a question of finding a basis, that's week 4. So that is why we keep the portion as week 1 to week 8. If we give you the basis, then the problem solving becomes simple after that, right? Means I'm just giving an example.
Madam,
Checking whether something is a subspace or not, finding its dimension.
It's all interconnected, I guess.
Yeah, that is the reason why we say the syllabus is from 1 to 8.
Linear transformations is a tricky thing, madam. Is there a possibility to place some special attention on that one? That was a killer for me.
Yeah, we will do matrix of linear transformation, all that in detail.
Yeah.
Means it's a revision session, so you're expected to know everything and we will just revise. Yeah.
The problem is my score was so bad, I don't think I know anything. That's it.
You can ask any doubts that you have.
Sure, sure. Thank you.
On that change of basis for linear transformation, also that lecture example, I'm not able to understand if that can be explained also.
Yeah, sure.
Thanks.
So yeah, for tomorrow's session, please go through the previous all the topics so that it will be easy. We'll not spend time unnecessarily. You can watch the previous live session videos go through the activity questions, solve with us and all that, so that it will be easier. We won't be wasting time.
Ma'am, you are going to take tomorrow's session, no?
Yeah, tomorrow and Friday also mostly. Okay then. Good night.
Thank you. Good night.
Thank you. Good night.
Good night, ma'am.
Good night, ma'am.
Good night, ma'am.
Good night.
Thank you.
Thank you, ma'am.
Yeah, good night.